Chapter 8, Section 8.1, Distribution of Sample Mean, Part 1. Lesson objective: describe the distribution of the sample mean, samples from normal populations. Statistics such as X bar are random variables since their value varies from sample to sample. As such, they have probability distributions associated with them. In this chapter, we will focus on the shape, center, and spread of statistics such as X bar. Now, if you recall, shapes can be described as skew left, skew right, and bell shape. We measure the center by the mean, median, or mode, and we measure spread by the standard deviation or the IQR. The sampling distribution of a statistic is the probability distribution of all possible values of the statistic computed from the sample of size n. The sampling distribution of the sample mean X bar is the probability distribution of all possible values of a random variable X bar computed from a sample size n from a population mean mu and standard deviation sigma. Now, this seems like a lot to take in. We'll look at some examples and break this down to where it makes sense. To illustrate a sampling distribution, we'll go through these three steps. Step number 1, you obtain a simple random sample of some size n. You compute the sample mean for that one sample. And then the third step, assuming that we are sampling from a finite population, we keep repeating steps 1 and 2 until we have all simple random sizes of size n have been obtained. Let's look at an example. In this example, we're going to use pennies. The weights of pennies minted after 1982 are approximately normally distributed with a mean of 2.46 grams and a standard deviation of 0.02 grams. Approximate the sampling distribution of the sample means by obtaining 200 simple random samples of size 5 from this population. Now, what we're going to do is we're going to compare the sampling distribution to the original population. The data on the following slide represent the sample means of 200 simple random samples of size n equals 5. For example, the first sample of n equals 5 had the following data. So we have 5 pennies here. We weighed the 5 pennies and we have 1, 2, 3, 4, 5 different weights. Then we take these 5 numbers and we find the average. That's our X bar. So our sample size is 5. We do this 200 times. We have 200 different sample means. Here's the display. Now, our first step is, what if we take these 200 X bars and we find the average? We find the mean of all these sample means. What would it be? And what if we look at the standard deviation of this 200 samples? And what if we looked at the shape of these? What would it be? The mean of the 200 sample means is 2.46. It's the same thing as the mean of the original population. The standard deviation of the sample means is 0.0086, which it actually got smaller than the standard deviation of the population. And as far as the shape, if we look at the histogram of the sample means, this is what it looks like. So as we can see, it's bell shape. So if we're going to talk about the shape, the center, and the spread of these 200 sample means, its shape is bell shape, normal. Its mean is the same thing as the population mean, and its standard deviation got smaller. What role does n, the sample size, play in the standard deviation of the distribution of the sample means? Well, as you'll see in the next couple of videos, as the sample size gets larger, we do not expect as much spread in the sample means, since the larger observations will offset the smaller observations. So let's try another example. Approximate the sampling distribution of sample means by obtaining 200 random samples of size n equals 20 from a population of weights of pennies minted after 1982. So if you recall, our mean is 2.46 and our standard deviation is 0.02 grams. This is the distribution of the sample size of 20 we see it still has the mean as the population mean, but the standard deviation got smaller. The mean of the 200 random samples for n equals 20 is still 2.46, but the standard deviation now is 0.0045, and it was 0.0086 when n equals 5. So as expected, there is less variability in the distribution of the sample means with n equals 20 than with n equals 5. Let's look at another example. This is the normal distribution for IQs. It is bell-shaped. It has a mean of 100 and a standard deviation of 16. Now let's look at the sampling distribution of the sample means, in this case, where our sample size is 4. We have a new shape. It's still bell-shaped. Its mean is still 100, but notice that the standard deviation has decreased. It went from 16 to 8. And let's look at part C. What if we look at this sampling distribution of sample means for n equals 16? It is still bell-shaped. Its mean is still 100, but again the standard deviation has decreased. This time it decreased from 16 down to 4. Now eventually there will be a formula to actually compute the standard deviation of the sampling means. Let's look at the notation. The mean of the sample means. If I take all the little sample means x bar and average those sample means, it's equal to the population mean. The standard deviation of the sample means gets smaller. So here's the notation. So if I'm looking at the standard deviation of all the little sample means, x bars, it is equal to the population standard deviation divided by the square root of n. And this is known as the standard error. So the mean and standard deviation of the sampling distribution of x bar looks like this. If we choose a simple random sample of size n, and the original population is mu and the standard deviation sigma, then the sampling distribution of x bar will have a mean equal to the population mean, and the standard deviation will be smaller. How much smaller? Well, we take population standard deviation and divide it by the square root of n. The standard deviation of the sampling distribution of x bar is called the standard error of the mean, and this is the notation. What's the shape look like? Well, if the random variable x is normally distributed, the distribution of x bar, the sample mean, is normally distributed. Let's look at our last example. What is the probability that a simple random sample of 10 pennies minted after 1982 we obtain a sample mean of at least 2.465 grams? So we're going to look at the sampling distribution. First of all, we know x bar is normally distributed because the original population was normally distributed. We know that the mean of all the sample means is the same thing as the population mean, 2.46. We know that the standard deviation is smaller. We take sigma and divide it by the square root of our sample size, in this case 10, and we get a standard deviation called the standard error of 0.0063246. We want to compute the probability of getting at least 2.465 grams. At least means greater than, so this is the area that we want. We know our mean is 2.46, so all we have to do now is change this to a z-score, and we can use table 5 to compute the probability. Using our z-score, we take x minus the mean divided by the standard deviation. 2.465 minus 2.46, we divide that by our standard deviation of the sampling distribution, and we get 0.79. So we want the probability of the z being at least 0.79. And again, table 5 gives us area to the left. We want area to the right, so we have to do 1 minus what's in the table, and we end up with 0.2148. Thanks for watching.